Hello everyone, I'm David and I'm going to give you a short overview over StRoM.
In recent years, we have seen a rapid increase in the available network bandwidth. At the same time, CPU frequencies have been stagnating. Given these two trends, the gap between the network bandwidth and the compute available on the CPU is widening further and further. As a result, more and more CPU cycles have to be allocated towards network processing, reducing the CPU time available for the application. This issue is intensified by the use of operating system network stack, which require frequent context switches between the application and the operating system. RDMA, Remote Direct Memory Access, is addressing these issues by completely offloading network processing to the network card. It also enables the network card to directly access the host memory. This means both the OS and the CPU can be bypassed, reducing the latency and the load on the CPU significantly. However, RDMA is not without its drawbacks. To explain this, we have to look a bit closer at the two operation types available in RDMA, one-sided and two-sided. The two-sided send-receive operations resemble the very common client-server abstraction. This abstraction is suitable to implement RPCs. However, it requires the remote CPU to be involved in the data exchange, introducing additional latency. In the case of one-sided RDMA, read and write operations can directly access the remote memory without involving the rebuilt CPU. This leads to the low latency that RDMA is known for. The drawback of one-sided operations is that it is non-trivial to make complex application-level operations to these basic primitives. This often results in multiple round trips over the network, negating the benefit of the low latency interconnect. In summary, between one-sided and two-sided, we have a non-trivial trade-off between performance and complexity. StRoM addresses these drawbacks and allows the application to deploy acceleration kernels directly on the remote NIC. As we see on the illustration here, the StRoM kernel has direct access to the host memory to retrieve or store data. It can also receive and transmit data over the network using RDMA. Given these capabilities of the StRoM kernel, we can mainly accelerate two types of operations. The first one are RPCs that are deployed on the remote NIC and can be invoked as one-sided operations. Secondly, we can accelerate data processing when data is transmitted or received. For each of these categories, we implemented two use cases. For data access, we first implemented the key value store get operation as a StRoM kernel. Deploying this kernel on the remote NIC reduces the number of round trips and the latency. In the second use case, we offload a consistency check to the remote NIC. This enables the consistent retrieval of data objects over one-sided RDMA. On the data processing side, we have a data shuffling kernel that partitions incoming data tuples on the fly. The hash function is implemented in the StRoM kernel. Each partition is written to a different location in the host memory. Data shuffling is a common operation in distributed applications to enable parallelism across cores or nodes. Finally, we implemented a StRoM kernel to gather statistics. In particular, we implemented hyperloglog to estimate the cardinality of a dataset that is received. Once the complete dataset has streamed through the StRoM kernel and is written to the host memory, the hyperloglog kernel will also write the estimated cardinality to the host memory. You can find more details about these four use cases and StRoM in general in the paper or the long presentation. StRoM is also open source and can be found on GitHub. Thanks for your attention.